Okay, welcome everybody to today's afternoon session. The first speaker is Professor Omri Sarig from the Weizmann Institute of Science, Israel. So he's going to speak on equidistribution of measures with high entropy for general diffeomorphisms. Over to you, Professor.
Thank you very much. Can you hear me well? Can you hear me well? I get no response. Can you hear me?
Okay. Yeah, I think everybody can hear you.
Oh, wonderful. Thank you. Thank you. So I'd like to thank Anish, Riddhi, and Aravinda for the invitation to participate in this meeting. I don't work, strictly speaking, in homogeneous dynamics, but I've spent all my career working on dynamical systems on non-compact spaces, and Professor Dani's work has had tremendous influence on many things that I did and am doing now. I think you will see this influence in today's lecture. I'm therefore very, very happy to be able to participate in an activity in honor of his work and legacy. I'm going to talk to you about the equidistribution of measures with high entropy for diffeomorphisms. Everything that I'm going to say is joint work, and here are my collaborators, Jérôme Buzzi, Sylvain Crovisier, and René Roux. And together we studied equidistribution for general diffeomorphisms. Now, before I tell you what we did, I'd like to start by recalling a few fundamental facts on Anosov diffeomorphisms. If you do not remember what is an Anosov diffeomorphism, think of a hyperbolic toral automorphism or a nonlinear perturbation of a hyperbolic toral automorphism. Anyway, that's 70% of the known examples. So everything starts with the following theorem of Sinai, which says that transitive Anosov diffeomorphisms have unique measures of maximal entropy. I'm going to call this unique measure of maximal entropy mu0, okay? It follows from this theorem that if you have an invariant probability measure mu, whose entropy is equal to the entropy of mu0, then necessarily the measure has to be equal to mu0. And one can ask, how robust is this statement? In other words, suppose you have an invariant probability measure mu, whose entropy is not precisely equal to the entropy of mu0, but is very close to the entropy of mu0. Does it then follow that this measure must be very close to mu0? This turns out to be a very fruitful line of investigation, because it turns out that there is a very, very strong and quantitative positive answer to this question. And this is the content of the next result, which is much more recent due to Shirali-Kadyrov. And what Shirali-Kadyrov showed was an inequality that I will explain in a short while. But before I show you this inequality, let me tell you what it says, loosely speaking. Loosely speaking, what Kadyrov's inequality says is that if the entropy of an invariant measure is epsilon close to the entropy of the measure of maximal entropy, then the measure itself has to be square root of epsilon close to the measure of maximal entropy, in the sense that when you compare the two measures on regular test functions, the results are order square root of epsilon away from one another. So here is the precise statement. Again, we are assuming that we have a transitive Anosov diffeomorphism. mu0 is the measure of maximal entropy. Mu is an arbitrary invariant probability measure. And let's assume that the entropy of mu is epsilon close to the entropy of mu0. Then Kadyrov tells you that the measure mu is square root of epsilon close to mu0, in the sense that when you evaluate the two functions on a test function, which is regular, so in this theorem, regular means Helder continuous, if you compare the values of the two measures on the same regular test functions, the results are square root of epsilon away from one another, okay? In particular, if you have a sequence of invariant probability measures mu sub n, whose entropies converge to the maximal possible entropy, to the topological entropy, then these measures must converge to the measure of maximal entropy. Moreover, this inequality tells you that the rate of convergence. The rate of convergence is square root of the distance from the square root of the difference between the entropy and the maximal entropy, the topological entropy. Okay, so these are two results for transitive Anosov diffeomorphisms. Now, what I'm going to do today in this talk is discuss an extension of these results to other diffeomorphisms, diffeomorphisms which are not Anosov. Now, why should one care about diffeomorphisms which are not Anosov? Because there are not so many Anosov diffeomorphisms. The only known examples of Anosov diffeomorphisms are either, as far as I know at least, either hyperbolic automorphisms on tori or hyperbolic automorphisms on nil manifolds, or perturbations of such systems. There are many manifolds on which we know that Anosov diffeomorphisms simply do not exist. Therefore, it is desirable to investigate these two properties, intrinsic ergodicity and effective intrinsic ergodicity, in the cadre of diffeomorphisms which are not necessarily Anosov. Okay, so that's going to be the topic of the talk. And here are the main results. So the first result is an analog of Sinai's theorem. It says that if you have a transitive C infinity, this means infinitely differentiable. If you have a transitive C infinity surface diffeomorphism with positive topological entropy, I don't want to deal with the identity map. So if you have a transitive C infinity surface diffeomorphism, then it has a unique measure of maximal entropy, which again, I'm going to call mu zero. So this theorem is divided into two parts. The first part is an existence result, and that is an old and very important theorem of Sheldon Newhouse from the end of the 80s, from 89. And the second part of the theorem is much more recent, and that's the uniqueness part. Now, notice that I'm not assuming that the diffeomorphism is Anosov anymore, but I am assuming that it is infinitely differentiable, C infinity, and I am assuming that the dimension of the manifold is 2. Okay. Now you cannot remove any of these assumptions. If you remove the C infinity assumption, then existence may fail. Okay. So there are examples of CR diffeomorphisms with arbitrarily high R, which do not have measures of maximal entropy at all. I believe the first examples of this type were constructed in dimension 4 by Michal Mizurevich, and in dimension 2 there are examples by Jerome Buzzi. So if I relax C infinity to CR, the theorem fails already on the level of existence. By the way, existence doesn't require the assumption of the dimension. It holds in any dimension. However, if I remove the assumption of the dimension, then uniqueness fails. It's very easy to construct examples of diffeomorphisms on free manifolds, which have many, many different measures of maximal entropy. So I cannot remove the C infinity assumption, and I cannot remove the dimension assumption. Okay, but I can remove the Anosov assumption, and that's what I was after. Okay, so this is the first result. We have intrinsic ergodicity. There is only one measure of maximal entropy. The next result, the one that I'm going to focus on in today's talk, is Kadyrov's inequality. It's not only that the measure of maximal entropy is unique, it's also that every measure with approximately maximal entropy is approximately equal to the measure of maximal entropy, and everything is quantitative. If the entropy is epsilon close to the maximal entropy, then the measure is square root of epsilon close to the measure of maximal entropy, in the sense that when you compare the two measures on the same test function, you get results which are square root of epsilon away. Here, test function means Helder continuous function on the manifold. Okay, so these are the two results that I would like to discuss today, and I'm going to focus on the second one. Okay, what is the difficulty? What is the difficulty in passing from Anosov diffeomorphisms to general diffeomorphisms? To answer this, let me briefly review, well, not exactly review Kadyrov's proof, but at least review his approach, his line of attack. So suppose we want to prove Kadyrov's inequality, this inequality star, and we want to do it for Anosov diffeomorphisms. We know that Anosov diffeomorphisms have finite Markov partitions. Okay, this is a result of Sinai and of Bowen. And moreover, we know that you have Markov partitions which lead to symbolic models which are transitive. So we can code Anosov diffeomorphisms by transitive subshifts of finite type. Okay, transitive means that there is a dense orbit. Okay, we can code Anosov diffeomorphisms by transitive subshifts of finite type, and therefore, to prove Kadyrov's inequality, it is sufficient to work with subshifts of finite type. Okay, and that is exactly what Kadyrov did. He proved his inequality for transitive subshifts of finite type, and then used symbolic dynamics to deduce it for Anosov diffeomorphisms. So let's try to use the same approach to deal with general diffeomorphisms which are not necessarily Anosov. Well, I proved already 10 years ago that there are countable Markov partitions. However, my countable Markov partitions did not lead necessarily to transitive symbolic models. Later, together with Jérôme and Sylvain, we were able to construct Markov partitions which do lead to transitive symbolic models, and therefore allow us to code general surface diffeomorphisms with positive topological entropy in terms of transitive countable Markov shifts. Okay? So notice the difference between the case of general diffeomorphisms and Anosov diffeomorphisms. For Anosov diffeomorphisms, you can do the coding using a subshift of finite type, which has a finite alphabet and is defined on a compact space. But for general diffeomorphisms, you need to use countable Markov partitions, which lead to countable Markov shifts, which are defined on non-compact spaces. Now, why do we have to use countable Markov partitions? Why are finite Markov partitions not enough? Well, perhaps the easiest way to understand this is to realize that subshifts of finite type are countable in cardinality. There are only countably many different subshifts of finite type. And therefore, the systems which are coded in terms of subshifts of finite type can only have countably many different values of topological entropy. And indeed, Anosov diffeomorphisms, it's well known, they only have countably many different possible topological entropies. However, general diffeomorphisms have a continuum of different possible values of the topological entropy. And therefore, the world of subshifts of finite type is simply not rich enough to capture all the possible dynamical behaviors already on the level of the values of the topological entropy. So countable Markov partitions are really forced on us. The space of maps with the finite Markov partitions is simply not rich enough. Okay. Okay, so we really have to work with the countable Markov partitions, and now we have a reduction of Kadyrov's inequality from the case of general surface diffeomorphisms to the case of transitive countable Markov shifts. And now comes the difficulty. The difficulty is that it's simply not true that every countable Markov shift satisfies Kadyrov's inequality. There are counterexamples. Okay, and I will show you some of these counterexamples later on. So that's the difficulty. What's written here in red, Kadyrov's inequality is simply false for general countable Markov shifts. By the way, the first person to notice this or to construct examples that violate Kadyrov's inequality was Sylvie Rouet, and we will return to her work later on. Okay, so since general countable Markov shifts do not satisfy Kadyrov's inequality, if we want to prove Kadyrov's inequality for diffeomorphisms, we have to answer two questions, okay? So the first question is, which countable Markov shifts do satisfy Kadyrov's inequality? And the second question is, which diffeomorphisms have symbolic models which belong to this class of distinguished countable Markov shifts which have Kadyrov's inequality, okay? So again, first question is, which countable Markov shifts satisfy Kadyrov's inequality? And the second question is, which diffeomorphisms can be coded in terms of these good countable Markov shifts? Now, these two questions are rather different. I mean, the first question is a question in abstract symbolic dynamics. You work in the cadre of countable Markov shifts, and you try to characterize those which satisfy Kadyrov's inequality. The second question is not a question in symbolic dynamics per se, it's a question in smooth dynamics. What you have to do is to come up with a dynamical property for diffeomorphisms which guarantees that they have countable Markov partitions which lead to symbolic models which lead to a countable Markov partition coding with Kadyrov's inequality. Okay, so the first question, the one in symbolic dynamics, is joint work with René Roux. The second question in smooth dynamics is joint work with Jérôme Buzzi and Sylvain Crovisier. Okay, so what I plan to do in today's talk is just to discuss these two questions and tell you what we know about them. So let's start with the first question, which is a question on abstract countable Markov shifts. The question is, which countable Markov shifts satisfy Kadyrov's inequality? And there is an answer, there is a very clean answer, and the answer is that these are exactly the countable Markov shifts which satisfy a condition called strong positive recurrence. Okay, so let me tell you what this condition is. Okay, so what is the strong positive recurrence condition? Okay, let me start with just a little bit of setup. First of all, what is a countable Markov shift? I should say at least once. A countable Markov shift is obtained in the following way. You start from a countable directed graph. So you have countably many vertices and they are connected by edges with directions. And then you consider the space of paths by infinite paths on this graph, where a path is a sequence of vertices which are connected by edges going in the right direction, okay? So how do you get countable Markov shifts from countable Markov partitions? You start from a countable Markov partition, and then you build a graph. The vertices of the graph are the elements of the partition, and you put a directed edge from partition element A to partition element B if the image of A overlaps B. Okay, so this gives you a directed graph, and then you build a countable Markov shift, which consists of all by infinite paths on this graph. That is to say, all by infinite sequences or vertices connected by edges going in the right direction. So this is a space of sequences. There is a natural action of the left shift mapped on it. And there is also a natural topology, which is generated by the base of cylinder sets. And usually, unless you have silly degeneracies, the result is a non-compact space. And that is the main difference between countable Markov shifts and subshifts of finite type, which are obtained from finite directed graphs and which are defined on compact spaces. So in the countable Markov shift world, the underlying space of trajectories is not compact. Okay. Now, a general countable Markov shift can be something very, very wild. For example, if you take the full shift on a countable alphabet, you get something which has infinite entropy. That's irrelevant for Kadyrov's inequality. Okay, the entropy has to be finite in order for us to be able to state Kadyrov's inequality. There is another pathology, and that is that even if you have finite topological entropy, maybe there is no measure of maximal entropy. Again, if there is no measure of maximal entropy, we cannot state Kadyrov's inequality. So for these reasons, I'm always going to make the following two assumptions. I'm always going to assume that my countable Markov shift has finite entropy, by which I mean that the supremum of metric entropies is finite. Okay, that's what I'm going to call the topological entropy or the Gurevich entropy of the shift. I'm always going to assume that the supremum of all metric entropies is finite. And I'm also always going to assume that the measure of maximal entropy exists. Okay, I have to make these assumptions, otherwise Kadyrov's inequality cannot even be stated. Now, these two assumptions are very, very strict assumptions from the point of view of the general theory of countable Markov shifts. There are many, many countable Markov shifts which violate these assumptions. However, when you discuss symbolic models of C-infinity surface diffeomorphisms, these assumptions are automatically satisfied. So from the point of view of the theory of diffeomorphisms, both these assumptions are very, very natural. You can always get symbolic models which satisfies these two properties. Okay, so suppose we have a countable Markov shift which satisfies these two standing assumptions. So we know that the measure of maximal entropy exists. Is it unique? Answer is yes. So there is a theorem of Boris Gurevich, a classical theorem which says that if the shift is transitive, if it has a dense orbit, then the measure of maximal entropy, if it exists, it's unique. Okay, good. That's good. But what's bad? What's bad is that it's not true that Kadyrov's inequality always holds. The problem is the following. It is possible, and the first examples was consulted by Sylvie Rouet, it is possible that there are shift invariant measures, mu sub n, whose entropies tend to the maximal entropy, but which escape to infinity, in the sense that the measure of every cylinder tends to 0. Again, it is possible, there are examples of countable Markov shifts with sequences of invariant measures, whose entropy converges to the maximal entropy, but which converge to infinity in the sense that the measure of every cylinder escapes to infinity. So here you see the first intersection with the homogeneous dynamics or non-compact spaces. Escape of mass to infinity is possible, it happens, okay? Now, why is this bad from the point of view of Kadyrov's inequality? Because imagine that you choose your test function to be the indicator of a cylinder, okay? Then mu0 of psi will be a positive number, the measure of maximal entropy of that cylinder. But mu n of the cylinder is going to tend to 0 because the mass escapes to infinity. The mass of every cylinder tends to 0. So when you look at the left-hand side in Kadyrov's inequality, it tends to a positive number, which is mu0 of psi, okay? On the other hand, the right-hand side of Kadyrhov's inequality tends to 0 because by construction, the sequence of measures has entropies which converge to the maximal entropy, to the entropy of the MME mu0. So you get the opposite inequality in Kadyrhov's inequality, okay? So if you have escape of mass to infinity in a way that retains the entropy, so if you have sequences of measures whose entropies converge to the full entropy, but which escape to infinity, then Kadyrhov's inequality breaks down in a very dramatic way. Okay, So this is exactly what the strong positive recurrence condition is meant to achieve. Okay, so let me tell you now what this condition says. So I remind you that I can think of a countable Markov shift as of the space of paths on a directed graph. Okay, so let's fix a vertex A and let's look at all the loops at the vertex A, which are first return loops of length n. So what is a first return loop of length n? It's a loop, so it's a path that starts at the vertex A and ends at the vertex A after n plus 1 steps. And I would like the loop not to visit the vertex A in between. Okay? So you start at A, you end at A, but you do not pass at A in the middle. Okay? It follows from general theory, from results of Gurevich on general countable Markov shifts, that if the topological entropy, the Gurevich entropy, is finite, then there can be only finitely many first return loops at every vertex. Okay, so these numbers are always finite, and therefore we can collect them in a generating function. Okay, so let's consider the generating function of the numbers of first return loops of length n. Okay, all the coefficients are finite. Now let's evaluate this generating function at its radius of convergence. Okay, the result could be plus infinity. Okay, it could be plus infinity, but sometimes it's finite. I will say that the shift is strongly positively recurrent if the result is strictly bigger than 1. Okay, maybe plus infinity, but strictly bigger than 1. So again, I will say that a countable Markov shift associated to a directed graph G is strongly positively recurrent if for some vertex A, when you look at the numbers of first return loops at the vertex A, and you build the generating function of these numbers, and you evaluate the generating function at the radius of convergence, the result is strictly bigger than 1. Now, I'm sure that many of you ask themselves whether this depends on the vertex A. The answer is that the value of the generating function at the vertex does depend on the vertex A, but it turns out that the question whether this value is bigger than 1 or not does not depend on the vertex A. So this is an invariant of the collection of vertices. It doesn't change from vertex to vertex. Okay? Let me give you an example of a shift which is strongly positively recurrent. Yes.
Can you hear me? Yeah, I'm just disturbing you. But what is the relation between radius of convergence and this positive recurrence that you're talking of?
Okay. So,
I mean, why you are looking into the radius of convergence here?
I'm going to define, I'm defining the condition of strong positive recurrence, not positive recurrence, strong positive recurrence. I'm defining this condition by stipulating that the value of the generating function of the numbers of the first return loops at the radius of convergence is strictly bigger than 1. That's a definition.
Okay.
Okay. If your question is what is the relation between this and positive recurrence?
So I mean, I'm just looking into like what would be the concept behind, I mean, just the idea of strong positive recurrence with the usual recurrence that we have.
It turns out that strong positive recurrence implies positive recurrence.
Okay.
But it implies positive recurrence, okay, good question. Positive recurrence means that you have a stationary probability vector, you have a measure of maximal entropy, and the expected return time to a vertex A is finite. That's positive recurrence. Strong positive recurrence turns out to imply that not only is the expected return time to a vertex A finite, it's also that it has an exponential tail. Okay, it follows from this condition. I don't have time to explain why, but it's a significant strengthening of the positive recurrence condition you're thinking of. It gives you not just finite expectation for the first return time to the vertex, it also gives you exponential tails for the first return time to the vertex for the measure of maximal entropy. Did this answer your? Okay.
Yeah, thanks.
Okay, so now let me give you an example of a shift which is strongly positive recurrent and an example of a shift which is not strongly positively recurrent. Later on, I will state a theorem that says that strong positive recurrence is equivalent to Kadyrov's inequality, and therefore you will also see from this example an example of a shift with Kadyrov's inequality and an example of a shift without Kadyrov's inequality. So here is the example. It's called a bouquet shift. It's built from a base vertex depicted here in blue, and then I add to it disjoint first return loops, okay? So I start from a blue vertex, a base vertex, and I add to it arbitrarily first return loops, which do not intersect. And you can see that I have complete freedom in adding these loops. There's no combinatorial interaction between first return loops. So now I'm going to be very clever, and I'm going to decide that the number of first return loops of length n that I'm going to add is given by this formula, okay? So in this formula, the most important thing is the numerator, 2 to the power n. So I'm adding roughly 2 to the power n first return loops at the vertex of length n. I'm modifying this exponential growth slightly by this polynomial denominator, okay? And k is a coefficient, a natural number that I'm free to choose, okay? So what happens when I look at the generating function of these numbers? Since Ln grow exponentially fast, like 2 to the power n, the radius of convergence is going to be 1/2. So when I calculate the generating function at the radius of convergence, this 2 to the power n is going to cancel up to negligible terms. And the result is going to be that the value of the generating function at the radius of convergence is going to be roughly this sum. Now, this sum is a finite number, okay? Without the k, okay, if it's just this sum, it's a tail of a convergence series, and I chose 100 to make sure that this tail is strictly smaller than 1. If I choose k to be small, oops, what happened? I don't know what happened. Sorry. My apologies. Oh, here it is. Okay, so I chose this this 100 here so that the value of the generating function at the radius of convergence is given by this tail. If k is equal to 1, then the net result is less than 1, and I get a shift which is not strongly positively recurrent. This shift will not satisfy Kadyrov's inequality. If, on the other hand, I choose k to be huge, so huge that this product is bigger than 1, then I get a shift which is strongly positively recurrent, and I will soon claim that this shift does satisfy Kadyrov's inequality. Okay, so you see that you have examples which are SPR and examples which are not SPR. Okay, so here are the two main symbolic results of this talk. The first one is joint work with René Roux. The second one is not our result, it's the result of Sylvie Rouet. So the first result is that the SPR condition is a sufficient condition for Kadyrov's inequality. If the SPR condition holds, then Kadyrov inequality holds. So the question, what is the condition we need to verify to be sure that Kadyrov inequality holds, has an answer, and the answer is we need to check strong positive recurrence, okay? The second theorem, which is due to Sylvie Rouet, is the converse. It says the following thing. It says that if the shift is not SPR, then you can construct a sequence of invariant measures whose entropy converges to the full entropy, but which escape to infinity in the sense that the measure of every cylinder tends to 0. As I explained before, this is an obstruction to Kadyrov's inequality. So shifts with such measures do not satisfy Kadyrov's inequality. So together, the two results say that Kadyrov's inequality is equivalent to the SPR condition. Okay? We have complete equivalence. Okay, so unfortunately, the SPR condition is not easy to check because it requires deep understanding of the combinatorial structure of the graph. And when you deal with symbolic models of smooth maps, often such information is simply not available. Okay, so this condition, even though it's a necessary and sufficient condition, which makes it good, is not easy to check, especially if you don't understand the graph deeply. Therefore, I would like to restate this condition in slightly softer way using entropy structure, and I'm going to use the idea of entropy at infinity, which is familiar to many of you, okay? Because this is an idea in some sense which originated in a community of homogeneous dynamics. I'd like to mention the works of Einsiedler, Lindenstrauss, Philippe, and Venkatesh, results by Ilya Chalyutin, results by René Roux, results by Fabrizio Polo. Okay, this result of entropy at infinity and using it to control escape of mass to infinity is very familiar to many people in today's audience, and it's also going to play a significant role in what we are going to do. So what is entropy at infinity? I'm going to say that the sequence of measures escapes to infinity if the measure of every cylinder tends to 0. Okay? And I'm going to define the entropy at infinity as the lim sup of the entropy as the measure tends to infinity. In other words, what you do formally is you look at all sequences of measures which escape to infinity, you look at the lim sup of their entropies, and then you take the supremum of all possible sequences. So again, you take an arbitrary sequence of measures which escapes to infinity in the sense that the measure of every cylinder tends to 0. You look at the lim sup of the entropies, and then you take the supremum of all possible sequences, and you get a number, okay? And I'm going to call this the entropy at infinity. And it follows from the two results which I stated in the previous transparency that the following three conditions are equivalent: strong positive recurrence, Kadyrov's inequality, and the condition that the entropy at infinity is strictly smaller than the maximal entropy. Okay? 1 implies 2 is my theorem with René-Roure. 2 implies 3 is triviality. Okay, if the entropy at infinity is equal to the full entropy, that exactly means that there is a sequence of measures which escapes to infinity while retaining full entropy. And as I explained before, this destroys Kadyrov's inequality. So not 3 implies not 2, and therefore 2 implies 3. And 3 implies 1 is Rouet's theorem. Rouet showed that if 1 fails, then there is a sequence of measures which escapes to infinity, but whose entropies tend to the maximal entropy, so that's exactly the contradiction of 3. Okay, so 1 implies 2, 2 implies 3, and 3 implies 1. All results are equivalent, and therefore we get the following answer to the first question. Which countable Markov shifts satisfy Kadyrov's inequality? Answer: exactly those whose entropy at infinity is strictly smaller than the full topological entropy. Okay, and that's the answer to the first question. Okay, now let's move to the second question, which is a question in smooth dynamics. And that question, which is a question on diffeomorphisms, asks which diffeomorphisms have codings in terms of countable Markov shifts, which are SPR, which satisfy Kadyrov's inequality. Okay, so before I give you the answer, I'd like to recall or maybe clarify exactly what I mean by coding, because that's going to be important. So what do I mean by coding? What sort of coding do I need to be able to reduce Kadyrov's inequality for a dynamical system to Kadyrov's inequality to the symbolic model? So here I have my diffeomorphism, F acting on a manifold M, and above I have a countable Markov shift. Sigma is the shift, okay? G is the graph, the directed graph. Sigma of G is the space of all paths on the graph. Sigma is the shift. So when I speak of coding, what I speak of is the existence of a countable Markov shift such that there is some commutative diagram of this form. Pi is the coding map. It goes from the symbolic space to the manifold, and certainly I would like the diagram to be commutative. I'm not asking for pi to be 1-to-1 and onto, okay? Because my pi's are usually going to be continuous, and this space is certain, which is totally disconnected, is certainly not homeomorphic to the manifold, okay? So I'm not going to ask pi to be 1-to-1 and onto. In fact, the pi's that I'm going to use are not going to be 1-to-1, and they're not going to be onto. So what do I need to ask pi to satisfy so that I will be able to reduce Kadyrov's inequality below to Kadyrov's inequality above? What I need is to be able to move at liberty from measures with positive entropy below to measures with positive entropy above without losing entropy. In other words, I would like every measure above to project to a measure below with the same entropy. And I would like every measure, at least with just a minute, I would like every measure with high entropy below to have a lift to a measure above with the same entropy, okay? And if this is my situation, then the measure of maximal entropy below has a coding in terms of a measure of maximal entropy above with the same entropy, and every measure below has with positive entropy has a lift above with the same entropy, and then I can reduce Kadyrov's inequality below to Kadyrov's inequality above. Okay, there was a question?
Yes, usually the map is from M to the shift, no? If you have a partition, then each point goes to its trajectory, no?
No. Okay, yes and no. So think about the, okay. Think about the following case, the decimal expansion of real numbers, okay? So if the number doesn't end, the decimal expansion doesn't end with 9s or with 0s, then the orbit of the point under 10x mod 1 remains in the interior of the partition elements, and you can do what you said. However, if the number ends with a sequence of 9s or with a sequence of 0s, then the orbit will eventually hit 2 partition elements at the boundary, and then you will have a choice. Okay, so this is exactly, so it is in fact much more convenient and more correct in some sense to move in the other direction. For every decimal expansion, there corresponds a real number. For some real numbers, there is more than one decimal expansion. This problem of boundaries is particularly serious when you code diffeomorphisms, because there you have partition elements which are all boundaries and no interior. Okay?
Okay, thanks.
Okay. Okay, so again, for me, a coding is going to be a commutative map where above you have a countable Markov shift, below you have the diffeomorphism. The coding map is not necessarily one-to-one, it's not necessarily onto, but it preserves entropy. Measures below have lifts with the same entropy above. Measures above have projections with the same entropy below. Okay, so such codings exist in very, very high generality. Suppose you have a C1 plus epsilon diffeomorphism with positive topological entropy. Let's fix some small parameter chi, which is positive. Now we can work at any dimension. I proved in dimension 2, and Ben-Ovadia proved, Snir Ben-Ovadia proved in any dimension that you can always find such symbolic codings in such a way that the map pi is finite to 1 on a set which contains a non-wandering set of the shift, and it has an image which has a full measure for all hyperbolic measures with Lyapunov exponent separated from 0 by chi. So in dimension 2, this implies all measures with entropy bigger than chi. And this is sufficient to know that measures above project to measures with the same entropy below, and measures below with entropy bigger than chi have lifts to measure above with the same entropy. Okay, so such codings exist in great generality. Indeed, Yuri Lima and collaborators have been able to construct such codings for interval maps, for maps with singularities such as billiard maps. I have a paper with Lima on flows. There is a result by Lima, Araujo, and Poletti on non-invertible maps with singularities. Countable Markov shifts, countable Markov partitions at this stage of time are known to exist in a huge number of scenarios. So this theorem has many extensions to maps which are not diffeomorphisms. So countable Markov partitions exist in many situations. That's the bottom line. There are also improvements of this theorem. For example, Mike Boyle and Jerome Buzzi have a version of this theorem with an injective coding if you fix the measure you wish to code. And Ben-Ovadia, Snir Ben-Ovadia has a strengthening of this theorem where you can precisely prescribe the coded set. For our story, the following improvement will be crucial, that if you have a C-infinity surface diffeomorphism, then you can build codings which are transitive. Okay, that will give us a transitive countable Markov shift. I need transitivity because I want my models to be intrinsically ergodic themselves, to have a unique measure of maximal entropy. Okay, so we have symbolic models in terms of countable Markov shifts, but we know that some countable Markov shifts do not satisfy Kadyrov's inequality, and therefore we have to understand which diffeomorphisms have SPR codings. Okay, SPR being the necessary and sufficient condition for Kadyrov's inequality, which I stated before. So again, there is an answer. The answer is again a strong positive recurrence condition, which again is going to be stated in the form of some entropy at infinity is going to be smaller than the full topological entropy. But now it's not clear what I mean by entropy at infinity. Why is it not clear what it means, what entropy at infinity means? Because it's not clear what one means by escape to infinity when the ambient space, the manifold, is compact. Okay? If you have a countable Markov shift, the underlying space is not compact, so it's clear what escape to infinity means. But if the ambient space is a compact manifold, what do we mean by escape to infinity? So this is exactly what I would like to explain now. Okay, what is the right notion of escape to infinity, which gives you the condition, a condition sufficient for the existence of a countable Markov partition, which leads to a symbolic model satisfying Kadyrov inequality. Okay, so how should I define escape to infinity for a diffeomorphism acting on a compact manifold? To do this, I need to give you a little bit of background on smooth dynamics. I'm not expecting everybody in the audience to know what I'm going to say now, but I don't want to, shouldn't be too worried, because I'm not going to say much more than the content of Oseledet's theorem, which I believe many of you know. I'm going to start with a definition, just a definition, okay? Not a statement, a definition. I'm going to define what it means for an initial condition to be non-uniformly hyperbolic, okay? So I'm going to define an initial condition, a point in the manifold, to be non-uniformly hyperbolic if, when you look at its orbit, fk of x, you can split the tangent space at each point of the orbit into two directions, two one-dimensional directions. One is called the unstable direction, the other one is called the stable direction. In the stable direction, the action of the map contracts vectors exponentially fast, and chi, the parameter chi, tells you how fast. Okay, so for every point in the orbit, fk of x, if you look at the tangent space and you look at the part of the tangent space which belongs to the stable direction, then vectors there are contracted exponentially fast at the rate chi. Okay. If you look at the unstable direction, you get exponential contraction in direction chi, but when you move to the past. Okay, so in the stable direction you have contraction in the future, in the unstable direction you have contraction in the past. In both cases, the rate of exponential contraction is this parameter chi. Okay, what is this parameter epsilon? The parameter epsilon affects the multiplicative constant in front of the exponentially decaying term, and it allows this multiplicative constant to deteriorate when you move from the point x to the point fk of x. Okay, it just says that the deterioration of the multiplicative constant is not too fast. It's controlled. It's a slow exponential decay. Okay. Finally, when you look at the angle between the stable direction and the unstable direction, well, this angle is positive because we have a direct sum, but this angle could tend to zero. But again, I would like this decay, this deterioration of the angle to zero, to be controlled. I want the angle, I'm allowing the angle to tend to zero, but I don't want this deterioration to be too fast on an exponential scale. Okay, so if I have a point which satisfies these four conditions, I call this point non-uniformly hyperbolic with parameters chi and epsilon. By the way, if I have an Anosov diffeomorphism, then every point is non-uniformly hyperbolic. Moreover, you can choose epsilon to be zero. Okay, but the difference between an Anosov diffeomorphism and a general diffeomorphism with positive topological entropy is that for general diffeomorphisms, you can take, this hyperbolicity is not uniform. Okay. Let NUH epsilon chi denote the collection of all initial conditions with these three properties. Now, at this point of the discussion, you can ask, is this set non-empty? Okay, I just made a definition. It looks like a very strong definition. How do you know that this definition is not vacuous? Okay, so at this point, enter two very important fundamental results in smooth dynamics. The first is the Oseledet's multiplicative ergodic theorem, and the second is the Ruel entropy inequality theorem. And both tell you that in dimension 2, if you have an ergodic measure with positive entropy, then not only is the set not empty, it's also a set of full measure. Okay, so this set has full measure for every ergodic invariant measure with entropy bigger than chi in dimension 2. Okay, this is a consequence of the Oseledet's multiplicative ergodic theorem, which I hope most of you know, and of Ruel's entropy inequality, which all of you should know. Okay. What I would like to stress now, and this is very, very important, is that the space of non-uniformly hyperbolic points is in some sense the set of points which satisfy the conclusion of the multiplicative ergodic theorem. This is a very, very bad set, okay? It's just a Borel set. It sometimes has empty interior, and it's certainly not compact. Okay, what you have below is a picture. Okay, this let me tell you what is this picture of. This is a picture of the phase space of a Hamiltonian, of a completely integrable Hamiltonian dynamical system with 2 degrees of freedom after a perturbation. So before the perturbation, the system is completely integrable and all orbits move on invariant tori in a way which is basically quasi-periodic, and entropy is 0. All measures have 0 entropy. After a lucky perturbation, maybe positive entropy is born. However, the situation is very, very inhomogeneous. Some initial conditions continue to move quasi-periodically on invariant tori. This is called KM phenomenon. And in this picture, the orbit closures of these quasi-periodic orbits appear like circles. Okay, this is what is called the KM tori. However, if the perturbation creates positive entropy, there is also something called the chaotic C, whose structure nobody really understands. It lies between these elliptic islands and is depicted here by this messy multicolored set, okay? If there is positive topological entropy, then there are measures with positive metric entropy, and they are all carried by this messy set called the chaotic C, and this is a very, very bad set from the point of view of topology. Okay, we do not expect it to have an interior, for example, and it's certainly not compact. Okay, it can accumulate on the elliptic islands where you have quasi-periodic motion, 0 entropy motion. Okay, so when you have a general diffeomorphism, situation is very, very inhomogeneous. You may have some orbits which only carry measures with 0 entropy, and the measures which carry chaos, the measures which carry positive entropy, are restricted to a very, very complicated non-compact Borel set, which in dimension 2 is this Borel set of non-uniformly hyperbolic points. Okay? So when we are going to talk about escape to infinity, in smooth dynamics, because we are interested in measures with high entropy for the purpose of Kadyrov's inequality, it is sufficient to look at the part of the space which carries these measures. This is a non-compact set, and we are going to define escape to infinity from the point of view of this bad non-compact set. That's the secret to everything, okay? The ambient space is compact, yes, but the ambient space is irrelevant to positive entropy because it also has orbits with 0 entropy, which only carry measure with 0 entropy. What is relevant is the non-compact part of the manifold, which where you have exponential sensitivity to initial conditions, and this set is not compact, and that's where we are going to talk about escape to infinity. Okay, that's if you want the most important idea of this talk, okay, to talk about escape to infinity in this non-compact subset, which is a very, very bad set from the topological point of view. Nothing better than Borel. Okay, maybe okay, nothing better than Borel. Okay, so how do you do this? How do you talk about the escape to infinity when your space is very, very bad? Okay, maybe it doesn't even make sense to talk about topology in this space. Well, you use general nonsense, and let me review this general nonsense very briefly. Suppose you have a measurable space, just a Borel space, no topology at all, and you want to define escape to infinity. So how do you do this? Use a structure that is called Bornology. You can also use an equivalent structure called ultrafilters if you prefer, okay? I find Bornology is easier to explain in talks. So what is a Bornology? A Bornology is just a way to specify which sets you call bounded and which sets you don't call bounded. So a Bornology is the collection of sets which you call bounded. It's a collection of sets and which satisfies the following axioms. The first three are very natural. Every point is bounded. A finite union of bounded sets is bounded, and a subset of a bounded set is bounded. Okay, very natural. Okay, if B is my collection of bounded sets, I certainly want it to contain all points. I certainly want it to be closed under finite unions, and I certainly want it to be hereditary. I want it to be closed under passing to subsets, because every subset of a bounded set has got to be bounded. The last axiom is not so self-evident, but I need it also. I would like every bounded set to be contained in a bigger measurable set, bounded measurable set. Again, every bounded set, I want it to be a subset of a bounded measurable set. Okay? If I have these 4 axioms, then I can speak of escape of infinity to measures. I will say that a sequence of measures escapes to infinity with respect to this Bernoulli if for every bounded set B, for every epsilon, there is a position in the sequence, whenceforth the measure of this bounded set is less than epsilon. Okay, again, a sequence of measures tends to infinity with respect to a Bernoulli if for every epsilon, if for every bounded set B, for every epsilon, there is a position in the sequence, whenceforth the measure of the bounded set is less than epsilon. Okay, very natural. The classical situation we have in mind is the topological setup when we have a locally compact second countable space, and we take our Bernoulli to be made of pre-compact sets. Why do I say pre-compact and not compact? Because I want everything to be closed under taking subsets, okay? Every subset of a compact set is pre-compact, but maybe it's not compact. Another example, which we have already seen in this talk, is the case of a countable Markov shift. And there we take as our Bernoulli the collection of bounded sets to be all sets that can be covered by a finite union of cylinders. Again, all sets that can be covered by a finite union of cylinders, we call these sets bounded, and we define escape to infinity using this collection. And now I come to the setup that I really want to talk about, smooth dynamics. Okay, I have this crazy set of non-uniformly hyperbolic initial conditions. And what are going to be the bounded sets on this set? Well, there are going to be sets which are called passing sets. Okay, so what are passing sets, or more precisely, subsets of passing sets? So what are passing sets? So here's the definition. I will call a closed set a passing set with the parameters chi and epsilon if there exists some constant C where you have these non-uniform hyperbolicity axioms with the constant C. Okay, so I remind you that a non-uniform hyperbolic point is defined by these properties for some C. If I fix the C, okay, I say C is always less than 100, and I look at all the subset of points with this particular C, and I take a closed subset of it, that's what I call a passing set. Okay, and I will define the passing Bernoulli with parameters chi and epsilon to be made of subsets of these sets. Okay, and that's a Bernoulli. So again, the space I'm interested in is the collection of all non-uniformly hyperbolic initial conditions with parameters epsilon and chi. Chi is the rate of exponential decay. Epsilon is the rate of deterioration of multiplicative constants along the orbit. A passing set, a bounded set, is a set where the C that appears here is specified. Okay, that's what I call a bounded set. For example, if you have a measure which sits on points where the angle between the stable and unstable direction tends to 0 almost surely, then it will escape to infinity because it will leave every bounded set by violating eventually condition 4. Okay, escape to infinity means deterioration of the bounds in non-uniform hyperbolicity. That's what this notion captures. Unfortunately, it really depends on the choice of chi and epsilon. There are various monotonicity relations between passing Bernoullis with different parameters, which I can never remember. It's an exercise for you to check them. I'm sure I cannot do it. Okay, so now finally I come to the definition of SPR for diffeomorphisms. It works for all C1 plus epsilon diffeomorphisms. I will say that a diffeomorphism is SPR if there exists a parameter chi such that for every epsilon, the entropy at infinity with respect to the chi epsilon passing Bernoulli is smaller than the full topological entropy. Okay, that's a property of a diffeomorphism. And it turns out that this is the right property. Okay, this is the right property. First theorem, if a transitive CR diffeomorphism is SPR, then it has a countable Markov partition, which leads to a symbolic model with the SPR property. Okay, so this is indeed the property that guarantees the existence of a countable Markov partition, which leads to a symbolic model with Kadyrov's inequality. So this is the condition that you need to check. And even more importantly, in fact, the main result is the second result, which is that you can check this condition. This condition is satisfied by all C infinity surface diffeomorphisms. This, if you want, is the main smooth result of today's talk. If you have a general transitive C infinity surface diffeomorphism with positive topological entropy, then its entropy at infinity is always strictly smaller than the full topological entropy with respect to the passing Bernoullis. And therefore, it has a symbolic coding, which is an SPR countable Markov shift, and therefore the symbolic model satisfies Kadyrov's inequality, and therefore the diffeomorphism satisfies Kadyrov's inequality. Okay, so a consequence of these two theorems, together with the theorem I stated before, with René Roux, that said that countable Markov shifts with the SPR condition satisfy Kadyrov's inequality, these three conditions prove the main result of this talk, which is that all transitive C-infinity surface diffeomorphism with positive topological entropy satisfy this inequality. So I see that I have 5 minutes left. Do I have 5 minutes left? Am I right? It's 60 minutes, right?
I have 6 minutes left.
6 minutes left, even better. Okay. So if I have 6 minutes left, I'll mention a couple more results. The first is that you can extend Kadyrov's inequality to Lyapunov exponents. If you have a transitive surface diffeomorphism with positive topological entropy, then it's not just that the measures are close in terms of the integral values on test functions, it's also that the Lyapunov exponents are close. If the entropy of mu is epsilon close to the entropy of mu 0, then it's also the case that the Lyapunov exponents of mu are square root of epsilon close to the Lyapunov exponents of mu 0. That's one result that I wanted to mention. It is curious that this result ends up being equivalent to Kadyrov's inequality and to the SPR condition. Okay, and the next result I wanted to mention was about the optimality of this inequality, because you may ask yourself, is this the best estimate that you can get? Maybe there is a tighter estimate. So there are two questions here. The first is about the exponent. Is the best exponent square root? That question was already posed by Kadyrov. And the second question is this the best multiplicative constant? And the answer is mixed. The answer is that yes, the square root is the best possible exponent. You cannot improve it further, but the constant is not optimal. Okay, so let me tell you what is the optimal constant and also how to show that the square root is the best possible exponent in this inequality. First of all, why is the constant not optimal? Well, it's very easy to understand why the constant is not optimal. The left-hand side of Kadyrov's inequality is invariant under the addition of coboundaries, but this multiplicative constant is not invariant under the addition of coboundaries. If you have a test function, which is the sum of a very small function plus a very big coboundary, then the difference of the integral values will not see the coboundary because it cancels out. But the coboundary can make the norm, the Helder norm, very, very big. So that's why the multiplicative constant is not optimal. If you want to get an optimal constant, you need to clean away the coboundaries. So how do you measure the size of a Helder continuous function modulo coboundaries? And the answer comes from probability theory, strictly speaking from the central limit theorem. It's a theorem joined with Jérôme Buzzi and Sylvain Crovisier, that if you have a transitive C-infinity surface diffeomorphism, then every Helder continuous function has asymptotic variance. So what is the asymptotic variance? You take the Birkhoff sum of the test function, and you measure their variance with respect to the measure of maximal entropy, and you pass to the limit. Now, why is this number interesting for our purposes? Because it doesn't see coboundaries. If you add a coboundary to psi, this coboundary gives you a telescopic sum contribution, and that telescopic sum cancels out when you divide by n. So the asymptotic variance doesn't see coboundaries, okay? By the way, the asymptotic variance can be shown to be smaller than a constant times the Helder norm, but the point is that it could be much, much smaller. For example, if the test function itself is a coboundary, then the asymptotic variance would be 0, even though the norm could be very big. Okay, so here is the optimal form of Kadyrov's inequality. Again, I'm assuming that I have a transitive, strongly positively recurrent C-infinity surface diffeomorphism. The optimal statement is that as long as you are talking about measures with high entropy, measures with entropy is delta away from the maximal entropy, then the inequality can be stated in this way. instead of the constant times Hölder norm, what you have is square root of 2 times the asymptotic variance. Okay, and that's the optimal constant, because you can show that you can always construct a sequence of invariant probability measures for which this inequality is in fact an asymptotic identity. The difference between the expectation values is actually asymptotic to square root of 2 times the asymptotic variance of the function. You can do this always, and this also incidentally shows that the square root is the optimal exponent. So bottom line is that the exponent in Kadyrov's inequality is optimal. The asymptotic, the multiplicative constant is not. The optimal multiplicative constant is square root of 2 times the asymptotic variance of the test function. And with this, I will finish. And of course, I will use this opportunity to congratulate again Professor Dani for his birthday and wish him many, many happy returns. Thank you.
Thank you for your interesting talk. Now, any questions or comments?
Omri?
Yes.
Do you see any transference from all the things that you told us today back to homogeneous dynamics, or?
I think that all the transference to homogeneous dynamics was already done by Einsiedler, Kadyrov, and company. These results, at our current point of understanding, are limited to dimension 2, which I think is trivial for you people. So no, at the moment I don't see new applications to homogeneous dynamics which were not done before. Really, the difficulty here is the inhomogeneous character of phase space for general diffeomorphisms, where you have mixture of different types of initial conditions.
And just out of curiosity, Kadyrov is Shirali Kadyrov.
Kadyrov is Shirali Kadyrov. Yes, yes. So the history of this thing, as far as I know, is I think the first one to prove an inequality of this form was Manfred Einsiedler for the angle doubling map. Then Fabrizio Polo in his PhD did subshifts of finite type with full shifts on finite alphabets, but I believe he got a slightly worse exponent than square root of 2. I don't remember exactly what his result. These type of inequalities are mostly important for homogeneous dynamical systems or non-compact manifolds, because then you can use them to control the escape of mass to infinity for measures with the high entropy. That's a program that Einsiedler, Lindenstrauss, Venkatesh, Philippe pushed very far. That's the history as far as I understand it. There are also results by Chayutin and by Ru, maybe other people.
Thank you.
Excuse me. I have a question about the. I have a very elementary question about your coding. I think the Kadyrov inequality contains some test functions, right? But I don't understand how do you correspond the function on the manifolds to a function on the shift space.
That's an excellent question. Thank you very much for this question. So one of the things which I wrote, but I didn't say, is that in these codings, the coding map is Hölder continuous. So if you look at it as a map between the subshifts of finite type, the countable Markov shift equipped with the natural metric to the manifold equipped with the natural metric, then this map is Hölder continuous. It follows that if you have a Hölder continuous map on the manifold, and lift it to the countable Markov shift by forming the function f composed with pi, that the lift is also Hölder continuous with respect to the countable Markov shift. So all Hölder continuous maps on the manifold lift to Hölder continuous maps on the shift. And that's how you can pass from a statement on Hölder continuous maps on the manifold to Hölder continuous maps on the shift. Okay? That's a very good question.
Any more questions or comments, whatever? Okay, there seems to be none. So let's thank the speaker.
Thank you.